அப்படின்னு அட்ரஸ் பண்ணணுமா மேடம்? நாங்கள் இதை பொசிஷன் முக்கியமா? சீனியர் போஸ்ட் டாக்டோரல் ரிசர்ச்சர் நீங்க சொல்லிடுங்க. சீனியர் போஸ்ட் டாக்டோரல் ரிசர்ச்சர். So otherwise ready ma'am. Now for 2 minutes to join madam. Sir, good morning.
Good morning sir.
Yes sir. Happy good morning சொன்னா I thought you were
இல்ல சார், அது நான் வேற ரூம்ல இருந்தேன், அதனால
I thought so breakfast ல இருக்கீங்களோ I didn't disturb.
ரைட் சார்.
Now fine.
ஸ்ட்ரீமிங் ஆரம்பிச்சாச்சு சார்.
நைஸ் சார். நீங்க அப்பா பெர்ஃபெக்ட். நீங்க அப்படியே வந்தீங்க. நான் ஒரு 2 minutes ஜாயின் பண்ணிக்கிறேன் சார். பிரேக்ஃபாஸ்ட் முடிச்சிட்டு வந்துடுறேன் சார். ஒரு 2 minutes மாஸ்டர் பண்ணுங்க.
என்ன யாரு அனுஷா லாவண்யா பேசவே மாட்டேங்கிறாங்க?
பாலு
சார். எஸ் சார், குட் மார்னிங் சார்.
வெரி குட் மார்னிங் மா.
பாலு
சொல்லுங்க சார். சொல்லுங்க.
நான் ஒரு இது அனுப்பியிருக்கேன் பாருங்க, லிங்க் அனுப்பியிருக்கேன் பாருங்க.
எது சார்? வாட்ஸ்அப்லயா?
இல்ல, மெயிலுக்கு அனுப்பியிருக்கேன். பிரீதா மேடம்.
ஹலோ.
பிரீதா மேடம், உங்களுக்கு ஃபார்வர்ட் பண்றேன், நீங்களும் செக் பண்றீங்களா?
எதுல மேடம்? இதுல சார்.
யூடியூப் லிங்க் ஒன்னு நான் அனுப்பி விடுறேன்.
சரி சார், நான் மொபைல்ல செக் பண்றேன்.
நான் அதை உங்களுக்கு ஃபார்வர்ட் பண்ணி விடுறேன், நீங்க பாருங்க.
எரர் ரெக்கார்ட்னு வருது சார். ப்ளீஸ் ட்ரை அகைன் லேட்டர்.
அப்படியே
ப்ளே பண்ணனும்.
நீ ஒரு அழகா வருதே சார், வந்துட்டு இருக்கு.
ஒரே நிமிஷம் சார், மறுபடியும் போடுறேன். எனக்கு எப்படி வருது ஒரு டைம்.
இல்ல, இப்போ நான் உங்க மெயிலுக்கு ஒன்னு அனுப்பி இருக்கேன் பாருங்க. மெயில
இல்லையே சார், எனக்கு ஓபன் ஆக மாட்டேங்குதே. நான் லேப்டாப் இதுல மொபைல்ல ஓபன் பண்ணி பார்க்கறேன். மொபைல் ஒர்க் ஆகுது சார், லேப்டாப்ல ஒர்க் ஆக மாட்டேங்குது.
அவ்வளவுதான். ரைட், ஃபினிஷ்ட். ஸ்ட்ரீம் ஆகணும். நம்ம இப்போ ஸ்ட்ரீம் ஆயிட்டு இருக்கு.
கேக்குது
சார், மொபைல்ல வருது சார்.
ஃபைன் ஃபைன், அவ்வளவுதான் மேடம். இப்போ நமக்கு குவைட்டா இருக்கலாம், சரிங்களா? ஏன்னா ஸ்ட்ரீம்ல இருக்கோம். ஆடியோ மியூட் பண்ணிடலாம்.
சூப்பர் இருக்கு. வருது சார் ஆன்லைன்ல.
ரைட் ரைட் ரைட். ஸ்டூடண்ட்க்கு குரூப்ல ஷேர் பண்ணிருங்க பாலு. பாலு, ஸ்டூடண்ட்ஸ்க்கு குரூப்புக்கு அதை ஷேர் பண்ணல. நம்ம ஏசிஹெச் கெமிக்கல் பரத் அந்த மாதிரி போட்டு மற்றவங்களுக்கு அதை இன்டிமேட் பண்ணிடலாம். பாஸ்கர் சாருக்கு அனுப்புங்க, அவருக்கு தெரிஞ்ச சர்க்கிளுக்கு அனுப்பிவிட்டோம்.
எஸ் சார். காப்பி பண்ணணுமா?
ஆமா, ஷேர் இல்லைன்னா காப்பி.
ஹலோ சார், நான் ராஜா பேசுறேன், தைவான்ல இருந்து. கேக்குதுங்களா?
ஏய் ராஜா.
ராஜா சார்.
சார் எப்படி இருக்கீங்க? எல்லாரும் எப்படி இருக்கீங்க? பிரீதா எப்படி இருக்கீங்க?
ஃபைன் சார்.
ராஜா, இது லைவ்ல போயிட்டு இருக்கு, அதனால நம்ம
எனக்கு தெரியும்.
ராஜா, இது ஸோ நம்ம லைவ்ல இப்ப போயிட்டு இருக்கிறதுனால கொஞ்சம் கேர்ஃபுல்லா பேசணும்.
மேம் பிரீதா மேம் எப்படி இருக்கீங்க?
சார் நல்லா இருக்கேன் சார், நீங்க எப்படி இருக்கீங்க? மேடம் எப்படி இருக்காங்க?
எல்லாம் நல்லா இருக்குங்க மேம்.
பையன் போட்டோ சூப்பரா இருந்தது. எப்படி இருக்கான் குட்டி பையன்?
நல்லா இருக்கேன் மேம், நல்லா இருக்கேன் மேம். எப்படி மேம் லாக்டவுன் எல்லாம் எப்படி?
லாக்டவுன் வீட்லயே போகுது சார். பக்கத்துல கொரோனா வந்துட்டு போயிருக்கு.
ஐயோ,
எங்க வீட்டுக்கு மாடி இல்ல சார், மேல இருக்கோம். நாங்க சேஃப், ஓரளவுக்கு ப்ராப்ளம் இல்லை.
ஓகே. எங்கள் வீட்டில் எல்லாத்துக்கும் வந்துருச்சு.
ஐயோ
அப்பா, பிரதர் ஒய்ஃபு, குழந்தை எல்லாத்துக்கும் வந்துருச்சு.
இப்ப எல்லாம் ரெக்கவர் ஆயிட்டாங்க
இப்போ எல்லாம் அப்படியே கொஞ்சம் கொஞ்சமாக ரெக்கவர் ஆகிட்டு வந்துருக்காங்க.
சரி
ராஜா
ரொம்ப வருஷம். திருமலகுமார் சார் ஓகே, லெஃப்ட் ஆயிட்டு. அலிசன் சார், நீங்க எதுவும் டாக் கொடுக்கியா?
நானா? நான் இல்லை சார், நம்ம இதுல நாமளே என்ன டாக் கொடுக்குறோம் சார்.
ஓகே ஓகே.
ரமேஷ் சார் வந்திருக்காரு. ரமேஷ் சார் வெல்கம். ராஜா சார்
சொல்லுங்க சொல்லுங்க.
நீங்க ஒரு பேப்பர் ஒன்று போட்டு கொடுத்துருக்கலாம்ல.
பாஸ்கர் சார் வாங்கிட்டாரு.
அப்படியா?
ஆமா, இதெல்லாம் நீங்களாம் இல்லை சார், நீங்களாம் வந்து பர்ஃபெக்ட் கிடையாது இல்லை அப்படின்னு
சொல்லிக்க மாட்டாரு.
ரைட் 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 சார். சார் கங்க்ராச்சுலேஷன்ஸ், நல்ல சிறப்பாக பண்ணிட்டு இருக்கீங்க.
எஸ் சார், எஸ் சார், தேங்க்யூ.
வெரி குட் வெரி குட் வெரி குட் சார். ஓகே ஓகே.
ஆஃபீஸ் போயிட்டீங்களா ராஜா சார்?
நீங்கள் லேபில் தான் சார் இருக்கேன். லேபில் இருந்து தான் பேசுகிறேன்.
லேப்ல இருந்து பேசுறீங்களா? ஆமா, உங்க டைப் ஆயிருக்கு போய் 10 மணி.
இப்போ 11:20 சார்.
11:20.
ஆமாம். இங்கேயுமே இப்போ டைவான்லேயுமே இப்போ செகண்ட் ரொம்ப அதிகமாக தான் இருக்கு. இப்போ மினி லாக்டவுன் மாதிரி போட்டிருக்காங்க.
ஓகே.
அதனால கேசஸ் அதிகமாகிட்டே தான் போகுது. டே பை டே டெத் ரேட்டுமே இன்க்ரீஸ் ஆகிட்டு தான் இருக்கு. கொஞ்சம் ஸ்ப்ரெட்டிங்கும் வந்து ரொம்ப ஃபாஸ்ட்டாக தான் இருக்கு.
ஏதோ மறுபடியும் புதுசாக ஏதோ ஒன்று கண்டுபிடிச்சிருக்காங்களாமே, போன எப்படியோ எங்கேயோ புது வேரியன்ட்டு.
இது அந்த நியூஸ் வந்து பர்ஃபெக்டாக இல்லை சார். அது ரீசன்ட் நியூஸ் என்னன்னா, வியட்நாமில் வந்து ஹைப்ரிட் வேரியன்ட் அப்படின்னு கண்டுபிடிச்சிருக்காங்க. அதாவது ஹைப்ரிட்னா இந்தியன் வேரியண்ட்டும் பிரிட்டன் வேரியண்ட்டும் ரெண்டும் காம்பினேஷனில் ஹைப்ரிட் வேரியன்ட் நம்ம சொல்லி புதுசாக கண்டுபிடிச்சிருக்காங்க. அது ரொம்ப ஃபாஸ்ட்டாக ஸ்ப்ரெட் ஆகுது வியட்நாமில் அப்படின்னு சொல்லியிருக்காங்க. அது லாஸ்ட் வீக் தான் அந்த நியூஸ் வந்துச்சு. எவ்வளோ வேக்சினேஷன் போட்டுக்கிறோமோ அவ்வளோ நல்லது தான் சார். ஆமாம். வேக்சினேஷன் முடிஞ்சதா? டன்னா?
இல்லை சார், நானே அஃபெக்ட் ஆகிற நிலைமையில் இருக்கேன். வேக்சினேஷன் போடுறது பார்த்துட்டு இருக்கு சார். இன்னும் 2 நாள் பார்த்துட்டு டெஸ்ட்டுக்கு போகணும்.
என்ன எப்படி சொல்றீங்க?
ஆமாமா, நான் தனியா தான் இருக்கேன். நான் எங்கேயும் போறது இல்லை. அதுதான் ஊருக்கு வந்தது. இங்க எங்கேயும் போறது இல்லை, வர்றது இல்லை. பக்கத்துல எங்க தாத்தா இருந்துட்டாரு. அங்க அப்போ ஒரு வந்துச்சு, அந்த கூட்டத்துல கிரியேட் ஆனதுதான் ஊர் ஃபுல்லா ஆயிடுச்சு.
ஐயோ ஐயோ.
அப்போ அங்கதான் இருந்தேன். நான் ஃபுல்லா அங்கதான் இருந்தோம் லாக்டவுன் முன்னாடி. அப்புறம் அவங்க வீட்டுல எல்லாத்துக்குமே ஆல்மோஸ்ட் வந்துருச்சு. ஒரு 20 days ஹாஸ்பிட்டல். இனிஷியலா போனதுனால பிரச்சனை இல்லை, ரெக்கவர் ஆயிட்டாங்க எல்லாமே. மாமா, 2 மாமா, எல்லாருமே. ஆமா, ஒரு 15 நாள் பார்த்தேன், பெருசா இல்ல. அப்புறம் அப்புறந்தே வந்து ஓரளவுக்கு தனியா தான் இருந்துட்டு இருக்கோம் எல்லாம் மோஸ்ட்லி. அதனால ஒரு தெரியல. இப்பதான் லைட்டா தொண்டை வலி இருந்துருக்கு. பார்க்கணும் எப்படின்னு. ஒரு 2 நாள் பார்த்துட்டு பார்க்கணும் என்னன்னு. அப்படியே இருந்துச்சுன்னா போயிட்டு வரோம். டெஸ்ட் எடுக்கணும். கடைசி நேரத்துல போய் எடுத்து ஒரு பிரயோஜனம் இல்லை. அதான் எடுத்துட்டு டெஸ்ட்டை பார்த்துட்டு வேக்சினேஷன் போடலான்னு இருக்கேன். வேக்சின் போட்டா பிரச்சனை எல்லாம் இல்லை, பிரச்சனை எல்லாம் இருக்கு, அது போட்டாலும்.
இப்போ என்னோட பிரதரே வந்து வேக்சினேஷன் போட்டாரு. வேக்சினேஷன் போட்டுட்டு நெக்ஸ்ட் டே ஃபீவர் இருந்தது. அது வந்து எல்லாருமே சொன்னது வேக்சின் போட்டால் ஃபீவர் இருக்கும் அப்படின்னு சொல்லி சொன்னாங்க. செகண்ட் டேவும் ஃபீவர் கண்டினியூ ஆச்சு. சரி அது சைடு எஃபெக்ட் தான் அப்படின்னு நாங்கள் அசால்ட்டாக வைப்போம். தேர்ட் டேவும் கண்டினியூ, ஒரு கன்ஃபியூஷனாக இருந்தது. அப்புறம் ஃபோர்த் டே போய் டெஸ்ட் எடுத்து பார்த்தா பாசிட்டிவ்.
இப்போ டெஸ்ட் பண்ணிட்டு தானே பண்ணியிருப்பீங்க?
இல்லை 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 அவர் ஒன்றுமே இல்லையா, கம்ப்ளீட் லாக்டவுனால வீட்டில் தான் இருந்தார்.
அதான் இப்போ ஒரு கன்ஃபியூஷன், வேக்சின் கொரோனா இருக்கும்போது பண்ணக்கூடாது வேக்சினேஷன்.
கொரோனா இருக்கும்போது வேக்சின் போடுறது இல்லை. ஆமாம், ஃபுல்லாக இல்லாதப்போ போட்டுருந்தோம், இல்லைன்னா ரெக்டிஃபை போட்டுருந்தோம்.
அதான் டெஸ்ட் பண்ணிட்டு தான் பண்ணணும்.
ஓகே 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 சார். அவன் சார் எப்படி போயிட்டு இருக்கு காலேஜ் லைஃப்?
Yeah, it is going well, sir.
Okay.
சார் குட் மார்னிங் ராஜா சார்.
சார் நல்லா இருக்கீங்களா?
நல்லா இருக்கேன் சார். ரொம்ப நாளாச்சு.
ஆமாம் சார்.
நல்லா இருக்கீங்களா? ஃபேமிலிலாம் நல்லா இருக்காங்களா? எல்லாரும் நல்லா இருக்கீங்களா?
எல்லாம் நல்லா இருக்காங்க சார், நல்லா இருக்காங்க. நீங்க எப்படி இருக்கீங்க? ஃபேமிலி எல்லாம் எப்படி இருக்காங்க?
விஜய் கணபதி அருளால நல்லா இருக்கேன்.
ஓகே சார். எல்லாம் கொஞ்சம் சேஃபா இருங்க சார். வேக்சின் போட்டாச்சா?
ஒரு வேக்சின் போட்டாச்சு சார், இன்னொன்று போடல. அது நான் 84 டேஸ்ன்றான். இப்போ
ஆமாம்
கிடைக்கல.
எல்லாத்துலேயுமே ஷார்டேஜ் தான் சார்.
சார் ராஜா சார், எங்க ஊர்ல இல்லை, ஒரு 2 நாள் முன்னாடி
வேக்சின். ஆமாம், வேக்சின் எல்லா இடத்துலையும் தான் இல்லை அப்படின்னு சொல்லியிருக்காங்க.
ஓகே சார், தேங்க்யூ சார், தேங்க்யூ வெரி மச்.
ரைட் சார், தேங்க்யூ சார்.
ஓகே சார். ரைட் சார். பலுசாமி சார், நல்லா இருக்கீங்களா?
சார் நீங்க எப்படி இருக்கீங்க?
நல்லா இருக்கேன். சீக்கிரம் போட்டுருங்க சார். இப்போ அதெல்லாம் இதெல்லாம் பயப்படாதீங்க. நானே பயந்துட்டு தான் இருந்தேன். அப்புறம் எங்க மைத்தான் சொன்னாரு, அதெல்லாம் ஒண்ணும் இல்லை மச்சான், நீங்க போடுங்க, அதெல்லாம் ஒண்ணும் கிடையாது. ஒரு 2 டேஸ் வந்து கொஞ்சம் ஃப்ரீயா நல்லா ரெஸ்ட் எடுத்தா எனக்கு ஒன்றும் ப்ராப்ளம் இருக்காது சார். கம்ப்ளீட்டா ரெஸ்ட் எடுக்கணும் சார். ஓகே சார். ஓகே, தேங்க்யூ சார். தேங்க்யூ.
ரமேஷ் சார், வெல்கம். ரமேஷ்
சார் வணக்கம் சார். பாஸ்கர் சார் வணக்கம். நல்லா இருக்கீங்களா?
வணக்கம், நல்லா இருக்கும். ப்ரோகிராம் நல்லா போயிட்டு இருக்கு. ஒன் டே நல்லா முடிஞ்சது.
ஓகே சார்.
செகண்ட் டே ஸ்டார்ட் ஆகுது.
சார் இவரு
ராஜேஷ் சார், குட் மார்னிங்
சார்.
ராஜேஷ் சார்,
டாக்டர் வெங்கடேசன் ஜாயின் பண்ணிட்டாரு.
டாக்டர் வெங்கடேசன்
ஜாயின் பண்ணிட்டாரு. நீங்க
டாக்டர் வெங்கடேசன் சார், குட் மார்னிங்
சார். குட் மார்னிங் டு ஆல் சார்.
குட் மார்னிங், வெல்கம் சார். வெல்கம்
சார். வெல்கம்.
Thank you
Nice
sir.
to meet you.
Nice to meet you too, sir.
Yes sir, nice to meet you. Yesterday we had a very good session, sir. Dr. Venkatesan, yesterday we had a very good session.
Okay.
Gone through the schedule. Yeah, it was inaugurated by Vice Chancellor Dr. Ramesh Goyal. We had a good session. In the afternoon, Dr. Wong from Malaysia, she spoke about hydrogen storage devices.
Okay.
All the sessions are interesting. We are biotech people, especially biotech people, are eager to
Sure sir.
learn from your lecture. It's a good participation, sir. Around 150 registrations were there.
Okay sir.
And then over 110 presentations are there.
Yes sir.
So we had a good time.
Yeah, it's because the most of the people during the pandemic situation,
Yeah.
so they are interested to join this kind of conference.
Time in the online,
Yeah.
yes.
Yeah.
They feel easy to join in the.
Yeah.
There's a slight change in the schedule, sir. So only Dr. Muthuraman speaks at 9:40.
It's fine sir. It's fine. No problem sir.
I hope we have just managed quickly.
It's fine sir. It's fine.
Sir,
I introduced Dr. Stanley, sir. Dr. Stanley, Senior Assistant Associate Professor in our department.
Okay, sir.
Dr. Stanley, sir. Sir is Dr. Venkateswara.
Yeah. Welcome, sir.
Yeah, thank you, sir.
Yeah,
Thank you very much.
Right. I'm Dr. Stanley from Applied Chemistry Department, sir.
Okay, sir.
Nice meeting you.
Nice to meeting you, sir.
In Balusamy, our department. Dr. Balusamy, can I try? Dr. Venkateswara.
Venkateswara, sir, this is Balusamy.
Okay, sir. Welcome, sir.
Yes, sir. Part of Applied Chemistry Department, sir. I'm working from 2016 onwards.
Sure, sir. Okay, sir.
Yes, sir.
HOD, sir, has joined. Good morning, sir. HOD Chemistry has joined.
Good morning, sir. HOD, sir.
Good morning.
HOD, sir, good morning.
I think, yes, joining shop.
Sir.
HOD Chemistry, no. Okay. Meanwhile, another faculty in our department, D. Preeta. Venkateswara, sir. Preeta, ma'am, you can introduce to Dr. Venkateswara.
Sir, good morning, sir. This is Preeta from Chemistry Department. Sir.
Yes.
Good morning, madam. Good morning.
Welcome, sir.
Thank you, ma'am.
Then we have Dr. Rajesh of Chemical Engineering. Dr. Rajesh.
Good morning, sir. Good morning, sir.
Vijay Lakshmi madam is also there. Chemical Engineering. Vijay Lakshmi ma'am.
Good morning, sir.
Good morning, madam.
Morning.
Sir.
Dr. Venkateswara ma'am.
Just wondering at looking at your profiles, sir. So many credentials. I don't know which one to mention and which one to read.
Okay, actually chemistry sir. Morning, sir.
Good morning, sir.
Actually, sir, now first lecture is by Dr. Venkateswara, sir.
Okay.
P. Venkateswara. Slide.
Yes, okay.
Dr. Muthuraman speaks at 10. That is 9:40. First here, Dr. Venkateswara starts.
Oh, yes. Nine o'clock நீங்க செஷன் ஸ்டார்ட் பண்ணிடலாம் நம்ம ப்ரோக்ராம் சரியா?
ஆமா சார். எஸ் சார். Papers நிறைய இருக்கு. Yes sir. Today we have several papers, more papers to make. நீங்க நிறைய papers இருக்கு சார்.
இல்ல இப்போ சார் இன்ட்ரோ யாரு?
இவர் Vijay Lakshmi ma'am. AC Dr. AC. Chemical. Already.
Sure. Okay. Shall I ring up to Maypan sir को ஒரு நிமிஷம் ட்ரை பண்றேன்.
Yes sir.
2 minutes.
That should be nice.
அவர் என்ன சொல்றாருன்னு பார்த்துட்டு then we can.
Okay sir.
I will try.
Yes.
விசில் அடிக்கிறது இங்கே அடிக்கா இல்லைன்னா நம்ம கூட அடிக்காங்க இங்கே அம்மா அழிச்சான் பேப்பர்லாம் ஒழிச்சு வச்சு டீமா செயல்பட்டு அவங்க பார்க்கணும்.
பாஸ்கர் சார் வரன்னு இருக்காரு. ஒரு 2 minutes வெயிட் பண்ணுவோம். கெமிக்கல் HOD said he will join.
Okay sir. Okay.
Right. நம்ம ஸ்டாஃப் யார் வரணும்?
I think So Anand Babu has to come. And then Preeta is there, Dr. Stanley is there.
Bhaskar sir, good morning.
Yeah, very good morning, sir.
Sorry, sir.
Good morning. Good morning.
சரி, அப்போ ஆனந்துக்கு நான் பண்ணிட்டேன், கால் பண்ணிட்டேன்.
Yes, sir. Yes, sir. Tirumala has come.
Okay, right. Probably they may be also trying, but anyway.
Tirumala sir, welcome. Good morning.
You have to join the meet link இல்லையா?
Actually, sir, good morning.
Good morning, Nachetan. Good morning, welcome. Vijayalakshmi madam is waiting. அவங்க தான் morning introduction.
Okay.
Good morning, sir.
Good morning. சொல்லிட்டு ஜாயின் பண்றேன்.
ACB ma'am, Vijayalakshmi ma'am. Can you please remind your faculty members, ma'am?
Yes, sir.
ACB, just to put a message in your group. Dr. Manigandan, welcome, sir, Annamalai University. Dr. Manigandan?
Sir, good morning.
Good morning, Manigandan. Welcome.
Good morning, sir. Thank you.
So Maniyan sir, today is on the session chair morning parallel track.
Yes, sir. He is in
Good morning, Dr. Maniyan sir.
Yes, sir. Yes, sir. Good morning, sir.
The video on பண்ணிட்டே நீங்க வரலாம். So that we can also see master உங்களுக்கு நல்லா தெரிஞ்சிருக்கு நாங்க பாக்கணும்ல.
Definitely, just a minute, sir.
Yes, sir. Yes.
Okay, sir.
Sir, Venkateswara sir, current area of work இதெல்லாம் இப்போ பண்ணிட்டு இருக்கீங்க.
Sir, can you hear me?
Yeah. What is the current area of research now you are concentrating now?
Actually, currently we are focusing on immune response based cancer therapy, sir.
Oh,
yeah.
So what are the compounds used for that? Just
because now we just use some cells to make like a nanoparticle. So this kind of nanoparticle, so is if you want to inject like a vaccine type, a SIN type.
Okay.
So maybe it will induce our immune system. So particularly will kill the cancer cell. So this kind of strategy, so we are focusing on, and other things like we are preparing some like anti-cancer based drugs, like some conjugated with some polymer, with some anti-cancer drugs to improve the efficacy. So this kind of research also we are doing.
Thank you, sir. Thank you. Maniyan sir, good morning. Vartikal. நம்ம நேர்ல மீட் பண்ண முடியலனா at least virtually now we are meeting.
Yes, sir.
It goes to our Dr. Bhaskar, who has made a lot of efforts.
Yes, sir. Very useful for all.
Yes.
This in the pandemic situation is very useful, sir.
Correct, because we are able to save time. So that means we are the traveling time and other things we are able to save.
Yes, sir.
Thank you. Sir, your area of current research.
Sir,
Maniyan sir.
Sir, the green chemistry and medicinal chemistry.
Great. So it is a need of our actually you are focusing on that.
Yes, sir. It's also very useful to learn.
Yeah.
Just now I introduced the green chemistry and the medicinal chemistry. Already I synthesized.
Okay. So yesterday during one plenary lecture by Dr. R. Velraj, Anna University, when you talked about
very useful.
renewable energy.
Yes, definitely. I completely listened that.
Oh, great. It's very inspirational. That's the need of the hour. Whatever he has.
The current situation, current scenario, sir. It's.
Ama. Bhaskar,
yeah, we can start, sir. Then let him join. Ama, sir. Already it is 9:10 now.
Okay, right.
Over to Anusha.
Yes, sir.
Sir, 1 minute, sir. Let us record.
Yeah, we have to record. Anusha, wait, we have to record.
Okay.
Start the recording. Who is recording, sir?
Sir, I am recording, sir.
Yeah,
okay,
nice.
Okay, fine.
Good, sir.
Asha, once it starts recording, you can start. Okay?
Okay, sir. Okay, sir.
You can see the red color record icon appearing at the top, right? Yeah, now you can start.
Okay, sir. A very good morning to one not present here. I cordially welcome you all to the second day of online international conference on green materials and renewable energy.
Now, I would like to call upon Ms. A.C. Vijayalakshmi, Assistant Professor, Department of Chemical Engineering, SVCE, to introduce the Chief Guest, Dr. Venkateswara, Senior Postdoctoral Researcher, Department of Chemistry, National Chungcheong University, Taiwan, and he will deliver a lecture with a duration of 30 minutes.
Thank you, Lavanya. It's my great pleasure and honor to welcome such an experienced postdoctoral researcher. Dr. Parthiban Venkateswaran is a senior postdoctoral researcher in the Laboratory of Nanomedicine and Drug Delivery in the Department of Chemistry, National Chungcheong University, Taichung, Taiwan. He had his post-graduation from the Tiruvallur University, his MPhil from the University of Madras, and his PhD from the National Chaitan University, China. He has a broad range of research areas which include the development of innovative and multifunctional nanocarriers, the mechanism of intracellular controlled drug release, anti-tumor effects of nanocarriers in vivo, anti-cancer drug design, mouse handling, IV injection, tail blood withdrawal and survival surgery, hyaluronic nanoparticle synthesis and conjugation with different anti-cancer drugs, polymer-based anti-cancer protein drugs, and so on. His current area of research is focused on the immune response-based cancer therapy. I really have a wide open eyes when I realize his expertise in handling the sophisticated instruments. The list goes on and on, along with the regular basic research instruments which we have used in our research like UV, and TLC. He also has an expertise in handling equipment like cell culture and live cell imaging, the Lexia confocal microscopes, flow cytometry, cancer cell in line staining and imaging, zebrafish live imaging, mouse handling, FTI spectrometer, zeta sizer, nano ZS DLS instrument, and so on. So, based on this list, it is quite obvious that his list of publications keeps extending day to day. He has a total number of publications of 31 in various peer-reviewed national and international journals, which has a total number of citations to be as 618 and a H-index of 60. He also has numerous presentations in various conferences, and it is our great honor to have you as a renowned guest here for the plenary lecture on day 2, sir. Welcome. I'd like you to take up the session, sir.
Thank you, ma'am. So nice introduction about me. So very good morning
to
pleasure, all.
Sir.
Very good morning to all. So first, I would like to thank to the department of the arranging the conference, the international conference, the Department of Applied Chemistry faculty members and the Department of Chemical Engineering faculty members. Now I'm going to share with my screen. Is visible, right?
Yeah, it's visible, sir.
Yes, sir, it's visible, sir.
Yes, sir.
And I must to say thanks to the former assistant professor Dr. Raja also. So today I'm going to share my topic is mesoporous silica nanoparticle based drug delivery for the cancer therapy. Before going to start, so just I'm going to talk about like I'm working as a senior postdoctoral fellow in NCHU So the university is like a very old university. So there is like 8 colleges department is there, and the university always welcome to the international student, especially in Indians, because the university has like a special fellowship, like specifically Indian students has a higher fellowships. So maybe in this lecture, so maybe some master students or maybe bachelor students will be learning these lectures, means maybe they are helpful this kind of information, because in this university maybe like they will give like a free tuition viewer fee and free dormitory for master students and bachelor students and doctoral students. And finally the scholarship also they are providing for some special scholarship like NCHU scholarship and the Taiwan government scholarship and TAGB scholarship. So this kind of scholarship also they are providing for the international student, and especially like for the only for Indian students also they are giving like special scholarship in specifically in NCHU university only. So maybe in future, so who has interested to join the master program or maybe like PhD program, maybe you would like to join with this university. This is the following link, so you can follow this. Sir, 1 minute I will use a laser point. So everybody know only for the cancer, but just to know when we know only for the cancer. What is cancer means? So in generally like a normal cells, like a normal division means just like maybe the cells are normal cells are damaged and again it will be repaired. So this is for like a immune system based normal cancer division. But in the cancer cell division means we cannot control. This is uncontrolled cell division. For example, maybe just like maybe if you can think here just like maybe one cells like a 4 cells, right? So maybe it will be like attached with the 2 cells, maybe it will attach like maybe like 3 cells. This kind of like uncontrolled growth is called as a cancer cells. But this is like a final stage, is a metastatic cancer. This one is like maybe the stage 4 cancer types. So this is called like a difference between the cancer cells and normal cells. According to the global data, so we can see like the cancer patients of the percentage, maybe we can see in the globally. So in the Asia part, maybe like 48.4% people are affected still in the 2018 global data. So we can see here the most of the people in Asia part only, so including in India also is affected in the most of the people in cancer patients. So next, the type of the cancer. We know only for like maybe several cancer, maybe like for example like a breast cancer, lung cancer and colon cancer.
Presentation, sorry to interrupt. Are you changing the slide?
I changing, sir.
Others could see, sir.
No,
Change
sir.
the slides.
No, sir. It's not representing.
Sir, presentation. Now it is okay, sir. Now we could see the slides, sir. Types of cancer, stages of cancer.
Okay.
Thank you, Mr.
Sir,
So
if you don't mind, can you enlarge the slide, sir? I'm not able to read the.
Sir?
Can you please enlarge the slide, sir?
Yeah, I enlarged, sir. I did like a full screen.
Sir, then can you please share the presentation screen, sir? That would be much more easier for you to change the slide.
I'm doing like this only, sir. So once again I will do it.
Slideshow should be better.
Sir, this is just like your entire screen. I will do that like this one. So just I can share this. Now you can see enter my screen, right? Sir, now we see.
Now it is okay, sir. Good. Now it is good.
So there is like 100 different known cancers that affect the human, but the most common cancer is like breast cancer and the lung cancer and colon cancer and the prostate cancer. So this type of cancer only maybe like initially we can find and we can easily recover the people. But some type of cancer like maybe like the stage like maybe 1, 2, 3, 4 layer like divided, but the initial stage like early stage and the localized stage we can easily find out and we can recover the cancer patient. But like a stage 3 and stage 4, so this one we can see the cancer affect like a more surrounding tissues. For example, maybe like a normal tissue also will affect it. So the stage 4 it's like is uncontrolled growth, right? So it is called like a metastatic cancer. So maybe one organ to another organ easy to spread. So this kind of stage 3 and the stage 4 is very difficult to recover the people, and this is types of cancer and these stages of the cancer. And what are the treatments are people are using? So there is like a 6 type of cancer treatments are available. Mostly the people like maybe initially maybe like surgery or maybe chemotherapy or hormone therapy and targeted therapy. These kind of treatments are available, but most of the people like using the chemotherapy treatment. But because why means because other treatments are there is some limitations, such as like surgery means maybe if you use like a surgery means maybe it's very difficult to recover the patient, and chemotherapy, so if you use like a chemotherapeutic drugs, so maybe it will affect like maybe some serious side effect, and there is some limitations such as like not good soluble, maybe like lifelong also will be very less. So hormone therapy and this kind of immune therapy may be like a cost effective, not like a cost effective. This is like a maybe expensive treatment, and this is not like easily available for in our country. And the targeted therapy and the radiation therapy is also like a very side effect. Side effects. Among these treatments, so just I focus on the chemotherapy. How do we improve? This is a chemotherapy drug limitation. So for example, we can see if like a person can take like a chemotherapeutic drugs, so maybe there is some serious side effect. And what is a disadvantage means there is a negative effect for the poor effectiveness and the many anti-tumor drugs, and the poor water solubility and the poor state limitation to overcome. How to overcome means maybe we will develop like a new type of drug delivery system, or maybe how to improve the this drug delivery mechanisms. This is very important for cellular uptake mechanism. So next, everybody know this what is a nano, right? So everybody know like a nanoparticle or nanotechnology. So we are using, many people are using nanotechnology, but we can see here. So if you like decreasing the size, so we can see initially the person like a 4-year-old, we can see the size, right? Different size, so we can see. But for example, the red blood cells or maybe virus, we can see on the microscope. So if we go to the less like a nanometer size, we cannot see. So using this particular instrument only, we can see. So this kind of technology, maybe it's like a more efficacy and a good like many advantages is available now. So maybe using this kind of technology, so we will use like maybe some cancer drug to prepare some drug delivery system. So using this kind of nanotechnology based drug delivery system as a like higher stability and the nanoparticle as a higher carrier capacity, it means like we can load like a more concentration of the cancer drugs, and easy to modify and easy to synthesize the nanoparticle, and easily is like a bio compatible and non-toxic and easy to store for a long time. This is advantage. Some polymeric nanoparticle has some limitations, such as it's like a maybe easy to drug will be released. We cannot control the drug loading capacities. This kind of some kind of polymeric nanoparticles are still available. Still they are optimizing the properties. So using this kind of nanotechnology, so already researcher developed many kinds of nanoparticles. So there is like a polymeric nanoparticle means maybe use like a dendrimer base or maybe like a micelle base, like these are These is are like just for a polymer based nanoformulation method, and this is a lipid based nanoparticle using like two kinds of, like one is hydrophobic and one is hydrophilic. So using like this kind of lipid solid nanoparticle, and a liposome based, this is like a lipid based nanoparticle. And inorganic nanoparticle means, so we use like ionic nanoparticle or mesoporosylica nanoparticle, and these are like many using the inorganic material formed like mesoporosylic nanoparticles. And finally, the carbon-based nanoparticle also like a carbon nanotube. So this is like a different kinds of nanoparticle. We can use a different kinds of application. Among these, I'm going to use like a mesoporosylica nanoparticle as a drug delivery strategy using a cancer therapeutic drugs. So why means, so why I choose like a mesoporosylica nanoparticle, and specifically in the mesoporosylica nanoparticle, I choose like a MCN40 kind. MCN41 is a one kind of mesoporosylica nanoparticle, because this one is like maybe we can see here this kind of nanoparticle. We can have like hexagonal structure. We can see like some porous, right? So this is a very advantageous for the drug loading. So these advantages is the large pore volume offer great capacity of the drug loading, and expectational mesoporous structure is easy to adjust, and we can easy to drug release and drug loading also, and easily modify the surface. So maybe we can use a different strategy to using this kind of surface modification and control the drug delivery strategy also. Next, how to synthesize this kind of mesoporosylica nanoparticle. For example, we can see this initially is like forming as a like a spherical micelle. After that, the spherical micelle is like arranged as a rod-shaped micelle. So finally, it's like a liquid crystal mesoporosylica nanoparticle. This is a pore, okay? This is a pore. After that, so we can use as a template of the silica material to make like a template. After forming as a template, just we will remove the template of the micelle. So once we remove the template of the micelle, we can get like a mesoporosylica nanoparticle. So this called like we can see as a pore and the hexagonal structure. So this kind of structure strategy, so we can use for the cancer therapeutic treatment. So this is using the chemical synthesis procedure. So using the C-tab, so using the base and the C-tab. So this kind of material forming as a micelle. So on the TUOS and the precursor silica. So just we will form like a first as a template form the silicon material. After that we will remove the template. So we can finally obtain the mesoporous silica structure, hexagonal structure with porous. So we can see like in the TM image, so we can see like hexagonal structure and like a porous. So this is a synthesis procedure of the mesoporous silica nanoparticle in generally. After that, once we prepare the mesoporous silica nanoparticle, the particle has a OH functional group. So the functional group, so maybe the mesoporous silica nanoparticle has a many surface modification we can easily modify, and using the different kinds of target and using the different kinds of fluorescent dye, and maybe like we use a different strategy. For example, stimuli responsive and reduction based, or maybe like enzyme responsive, or maybe like a light responsive. These kind of strategy, so we can modify easily in the mesoporous silica nanoparticle. After that, so once we form like a drug loaded mesoporous silica nanoparticle, how it will attain or maybe intake in the cells in the human body. So we can see here, so this one is like a normal cell, normal blood vessel. So normal blood vessel, so we can see the blue one is a mesoporous silica nanoparticle is just like a going. But if like only like a tumor site, we can see like this one is a EPR effect. In the tumor cells, we can see like some blood vessels as a gap. So in this particular gap, so maybe the mesoporous silica nanoparticle will go to intake the cancer cells, because so we use a target, right? So specifically the mesoporous silica nanoparticle specifically bind it to the cancer cell once, not like a normal cells. This is like a uptaking mechanism. After that, this is two kinds of targeting. So one is a passive accumulation, another one is an active accumulation. So this called like you can see the passive accumulation means, so maybe if we have like a tumor cells has like a blood vessel gap, so it automatically will be accumulated. This is like a passive accumulation. But active targeting means, for example, like different cancer cells has different kinds of cancer receptors, right? So, for example, like a folic acid has a specific receptor. Maybe in the cancer cell has like a folic acid receptor means, so specifically our designed mesoporosilicon nanoparticle as a cancer targeting means, like folic acid targeting means, so it will specifically bind it to the folic acid receptor. So this is called like a passive and active targeting. And another one is like how will be uptake and accumulated in the tumor cells. So we can see these healthy cells and the cancer cells. So first, initially the tumor tissue so accumulated in the blood vessels. After that, accumulated in the cancer cells. Finally, in the cancer cells, so using the different kinds of strategy. For example, here I'm going to talk about like a stimuli responsive means maybe disulfide bond cleavage or maybe like enzyme-based cleavage. So once the mesoporosilicon nanoparticle bond breaking means, so it's like going to the endosome reaction or maybe lysosome. So after that, finally we'll specifically target to the nucleus to damage the DNA structure. So this is the cellular uptaking mechanisms. Next, what are the strategies so we will use for the different kinds of drug delivery mechanism? So there is a many strategies that researchers are following. So here, just like a pH means maybe the cancer cell like a pH is like acidic condition, like a lysosome or maybe endosome like a 4.25 or maybe like a 5.2 6.5. This kind of different kinds of pH. Specifically, we use this kind of strategy to release the cancer drugs. And the redox potential means maybe we use some like a disulfide bond. So if we have like a disulfide bond, so the disulfide bond, if we have high concentration of GSH, the glutathione, so the disulfide bond once cleavage means, so we can see the drug will be released. This is like a redox potential based drug delivery strategy. This one is an enzyme. Maybe like particularly if you use like in the cancer cells, specifically in the cancer cell means like maybe the pH is acidic condition, maybe like some ROS is high concentration, and the enzyme also is a different concentration of enzyme. So this is a cancer cell and normal cells are different. So maybe we can easily using this kind of strategy to deliver our drugs. This is like internally because maybe in the cancer cell, so we know this is a strategy, so we will use this kind of internal strategy to deliver our cancer drugs. This is internal stimuli responsive drug delivery system. Another one is like external stimuli means, so we can use some like magnetic nanoparticle, and another one is like a photo ultrasound and UV light. So this kind of strategy, maybe we have to inject the drug. After that, the externally we have to give the responsive, then automatically the bond breaking or maybe like this kind of strategy will external. So maybe once give the external force, maybe it will be automatically damage or cleavage in the bond. So after that, the drug will be released to the cancer cells. This is the external stimuli responsive drug delivery systems. After that, so here I'm going to, this one is already published in my group. So this silicon mesoporosilicon nanoparticle synthesis procedure. So we using like a disulfide bond reduction based system. So here we can see initially we prepare like using the CTAP as a like this kind of mesoporosilicon nanoparticle. This one is silicon nanoparticle as OH functional group. So now I'm going to modify the surface. So using this kind of OH group, we can see here just I'm going to modify the surface is HH functionalized. After SH functionalized group, so I'm going to use like a redox responsive strategy. So this disulfide bond is like in the high concentration of GSH. The disulfide bond once cleavage means we can drug will be released. This is the strategy. After a disulfide bond with the NH functionalization, I'm going to use like a bulk protein. This is like a ion serum like a transferrin. So this kind of bulk protein. So this protein finally I attach with this silicon nanoparticle. After that, this kind of strategy, maybe I'm thinking maybe it's not good soluble. Maybe I'm going to improve the solubility means I'm going to use some PEG saline to improve the water solubility. So finally, I optimized the disulfide bond and the bulk protein, and finally I load the doxorubicin is a anti-cancer drugs. So this one is a cancer drug I loaded. You can see here the bulk protein once I attach with the mesoporosilica surface, so the drug won't come out, and the PEG also I attached on the surface. So here we can see this kind of system very clearly indicates the drug won't come out in the normal cells. Using this kind of material, So this proposed drug delivery system for the graphical abstract. So here we can see this mesoporous nanoparticle. So maybe once a specific receptor, right? This is I use like a transparent protein. So in the cancer cell has a many receptor. Maybe in this case, so maybe there is a transferrin receptor in the cancer cells. Once bind to the cancer transferrin receptor, after it will go to the endosome and lysosome. So it particularly as internally is like maybe millimolar concentration of the GSH. So the millimolar concentration, the disulfide bond once is cleavage means. So we can see the disulfide bond cleavage means this drug will be directly, because the doxorubicin is like a nucleus targeting drugs. So once it's like breaking the disulfide bond system, so the doxorubicin drug specifically target to the nucleus DNA structure will be cleavage. So this is the proposed mechanism of the doxorubicin loaded mesoporous nanoparticles in the redox stimuli system. This is after that we check the toxicity of the different cancer cells. So we can see this one is like MCF7 and breast cancer, and this is a colon cancer HT29. So initially the black one only for the mesoporous nanoparticle with finally transparent attached with the PEG. There is no drugs. And the red one is only for the free drug. The blue one is a drug loaded mesoporous nanoparticle. We can see without nanoparticle, without drug, so there is a no tox, because almost about 90% is there is a no toxic. And if I use like a free drugs, also is a toxic. But compared to the mesoporous nanoparticle, we can see about like 50% is toxic using a 100 microgram. So this kind of maybe you can see the same concentration if I use a free anti-cancer drug and the drugs loaded nanoparticle, we can see the efficacy is improving, right? So we use like this kind of strategy using a different the HT29 also. Comparing to the HT29 and this one, it's almost like a similar effect. But if I check within the normal cells, we can see, because the cancer cells already I know discussed, right? In the cancer cell, like high concentration of GSH, so disulfide bond once cleavage means drug will be released. This is a cancer cell. But in the normal cells, the GSH level, the glutathione level is not like a millimolar concentration. So that's why you can see the free dose is toxic in the normal cells, like around 40% cell death. But if you like a dose loaded nanoparticle and the without dose, so we can see that there is a no toxic, because this a normal cell is a no high concentration of GSH. After that, we measure the fluorescent microscopy to confirm like a nuclear, because a nucleus targeting drug, right? So we can see this one is a normal cell line, and we use a MCF cell line, the breast cancer and the colon cell, to check the drug release mechanism and the properties. So see here, so we cannot see any, because this one is like a red emission. We can see the normal cells, we cannot see any emissions. But once we use a cancer cell lines, so MCF cell and the HT29, we can see as a particularly not like in cytoplasm, only particularly it can show the emission and the nucleus. So this is like another evidence for the specific targeting drug delivery. We checked anti-tumor for the using the mice experiment. So here the tumor volume. So we can see that this experiment we contain like around 30 days. So this one is like we use 4 groups. One is a control, and the doxorubicin is a free anti-cancer drug, and without drug mesoporous nanoparticle, and the dox loaded mesoporous nanoparticle. We can see the pink one. So it means like usually the only for the control group there is a no drug, nothing, right? So it's like still the tumor size is growing. So you can see this the photographic image, the control, right? So you can see the tumor growth is like same, but once the dox loaded tumor growth we can see is decreasing, right? So it means like specifically the mesoporous nanoparticle in the cancer cells. So the disulfide bond once cleavage means it will be damage the DNA structure, so the cleave the cancer cells like this. So in the body weight, so we check the like side effects. So we can see there is no changes in the mouse weight. After that, the tumor weight also we can see. So in the control groups still is growing compared with the control group. So we can see the free dox compared with free dox, and the doxorubicin loaded mesoporous nanoparticle is almost is like a quench or maybe inhibit the tumor growth. So compared with the free dox. the efficacy is like maybe compared with the free dose, it's like a 62% is increasing. This is like this one is like a dicyl bond responsive based drug delivery system. So next one is like this one is like enzyme responsive based drug delivery system. So we can see like a similar strategy we are following, but using this as a same material, mesoporoxylic nanoparticle, but we use like a cyclodextrin as just because we need to the drug won't come out, right? So because previously I used like some protein to block the drug release, but here I'm going to use just like a organic molecule like a quinone moiety. So if only use like a quinone moiety is easily to drug will be released, so we can avoid to the drug leakage means. So I use like a cyclodextrin to cap means maybe drug won't come out. After that I use like a enzyme responsive strategy, use like a quinone moiety. So in this case, so in the specifically in the cancer cells as a like a NQO enzyme is like high concentration, maybe like once I have high concentration of this one, maybe due to the 2 electron reduction. So this kind of 2 electron reduction, maybe this bond will be cleavage. Once this bond will cleavage means after that the cyclodextrin will be easy to release. So after drug releasing, after the will release the cyclodextrin, so we can see the drug will be released to the cancer cells. This is an enzyme response based on the cancer strategy. After that, so because many paper and many researchers are only for the focusing on this kind of stimuli or like this mechanism, but this is like a new H2S based drug delivery system, because in generally in our body like H2S is like a third endogenous transmitter, but in this H2S is like produced in the three kinds of enzymes. For example, one is like cystathionine beta synthase and cystathionine amylase acylase, and the third one is that 3-MPST. These three enzymes like contained with the forming as a H2S. So in these three enzymes in the cancer cell is like uncontrolled growth, or means like uncontrolled volume, or maybe this kind of things in the cancer cells compared to the normal cell. So using this strategy, so we need to develop like a new drug delivery system in the H2S response. So here the CBS enzyme upregulated in the human colon cells, and the HCT116 and HT29 is a ovarian cancer. So this cell line, this kind of enzyme like overexpressing is higher level in the cancer cell lines. So using this strategy to develop a new material. After that, what is the important means? So this means because these other two enzymes we didn't focus, just only for the CSC, because if you use like a CSC means, so we know the colon cancer and the ovarian cancer is a higher expression. After that, this is a synthesis procedure and dose loaded mesoporoxylic nanoparticle. So we use like the same material mesoporoxylic nanoparticle to functionalize NH2 functionalization. After that, we use like a so maybe if we have acid group, so in the high concentration, the CBS enzyme, the acid will be reduction, become like NH2, then it will be like this strategy. So after that, the same, so we use a cyclodextrin to cap like a drug leakage. After the capping with attached with the cyclodextrin, so we use the folic acid receptor, because the cancer cell like many receptor, right? So specifically if you want to target with some specific cancers, so we have to use some specific target like as a folic acid. So in this strategy, so we use it as a folic acid receptor. After attached with the folic acid, this is a final molecule. So we can see here, this one is acid group, right? So maybe the high concentration of the H2S, maybe the acid will be become like NH2. After the NH2 means maybe the electron delocalization. So maybe this bond will be cleavage here. Once after the cleavage means that the cyclodextrin will be released and the drug will be released the strategy. After that, this a graphical abstract for the synthesis procedure. After that, we check the DLS and SEM image. We can see the particle size are really around 100 nanometer. After that, further we confirmed with the TM image. We can see then the TM image like a uniformed structure, the hexagonal. After that, further we confirmed the uniformed structure as like a pore volume and the surface and hexagonal diameter, everything is same or maybe different. So we confirm almost like same, and further we check using the XRD pattern, and this one is the TM image and the XRD data, almost a similar pattern in the surface diameter. Further we confirmed FTIR spectra also using the different functional group. We can see after surface modification the site, and we can see the site after the functional modification site will react, means maybe it's like disappearing. So this is a different functionalization confirmed with IR spectroscopy. Further we confirmed the solid state NMR. So maybe because we are not sure, maybe this kind of strategy maybe need to confirm only if IR data is not enough. Maybe further we confirm the solid state NMR to make sure the number of the carbons. After surface modification, further we need to make sure the BET experiment, like the surface, and BEG like a pore volume. So we can see here like initially only for mesoporous silicon nanoparticle with NH functionalization. After further modification, we can see the surface area is decreasing because of the functionalization or increasing, or maybe dye is loading. Further the pore volume also is decreasing because of, so we can see initially only for the NH2, further we attach with the NH side group. So that's why the pore volume also is slightly changing or maybe decreasing. Further we check the weight loss in the TG analysis. So we can see the figure A only for the mesoporous silicon nanoparticle. So for further we attach with the different functionalization, we can see the weight drug loading ratio also is decreasing because of figure D and E. So we can see why means because we added like some fluorescein dye to load the as a model drug as a fluorescein dye. So we can see the drug loading here also. After that we check a different functional group, right, we use. But here the zeta potential, the mesoporous silicon nanoparticle, initially the OH functional group is a negative, and after each functionalization we can see like a positive and negative charge. So this is a confirmation for the material conformations. Further we check like in the mesoporous silicon nanoparticle as a, like the pore volume and as a more high drug loader capacity, right? So we use this strategy to using a drug loading capacity experiment. So we can see here, so we use like a 0.5 and a 10 ratio, like this kind of ratio we use it to check so maximum drug loading capacity. So this one is like a 2:10 ratio is like a maximum, sorry 3:10 is like a maximum. Further we check the drug releasing experiment also. So in the drug release experiment, initially only for the PBS there is no drug leakage because some paper or maybe some of the drugs, like maybe if like a just like a 10% drug will be released like initially within 1 hour to like a burst release will be possible. But in our case is there is like only for up to 1 day 24 hours there is no drug leakage. After that we use slowly increasing the HTS concentration. We can see up to like a 5 millimolar concentration almost like within 5 hours. Within 5 hours like a 75% usual drug will be released. That we check the cell viability experiment. So HT29 and ELA cells. This is because this is a macrophage cell line. This is like a colon cancer. That because the colon cancer is high concentration of the H2S, but ELA cell like a macrophage cell line there is no H2S concentration. To make sure the H2S drug delivery system specifically in the colon cells as a drug will be released, or maybe you check like a ELA cell. We compare both cell line. Here we can see here the blue one and blue one like without drug loaded mesoporous silicon nanoparticle there is a 90% of cell viability. After drug loaded nanoparticle and the free drugs we can see almost the same efficacy. But here in the ELA cell no high concentration of H2S, right? So here we can see only for the free drugs only as a above 40% of toxic compared to other functional group. Next we demonstrate the live cell imaging using the different cancer cell line and normal cell line also. Here we can see that these are ELA cells and these two are like colon cancer. These two are means like A2780 and S/3 is like this is ovarian cancer cells. This is also colon cells. To make sure, so HTS concentration in the high level only for the colon cell or maybe ovarian cells or maybe in the HeLa cell, to make sure using this cell imaging strategy, we can see in the HeLa cells we cannot see the emission because no high concentration H2S in the HeLa cells compared to other two cell line. We can see here our high red emission is appear. Then further we confirm that the doxorubicin drugs are only for the nuclear targeting drug, right? So we have to confirm with some nucleus staining dye to make sure the drug specifically released in the nucleus or cytoplasm, to make sure using the some DAPI nucleus staining dye. So we can see here like HD29, HD these two cell line, we can see this one is specifically the blue emission appeared in the nucleus only. The same, the doxorubicin also is appeared in the nucleus only. So these results are clearly indicated. So the high concentration of the H2S, colon cancer and ovarian cancer only, our drug delivery strategy will release in the cancer cells. This is a graphical abstract for the drug releasing strategy. So here you can see this is a blood vessel, right? So in the blood vessel, like EPR strategy, because in the cancer cell has like some blood vessel gap, so there is a tumor metastatic state. Maybe once we inject to our drugs, so maybe the nanoparticle will flow like this. So maybe specifically bind to the cancer cells. After binding the cancer cell, we can see there is a we attach with the folic acid, right? So when the cancer cell has like a folic acid receptor, so our nanoparticle bind with the folic acid receptor. After binding with the folic acid receptor, it will intake to the inside the cancer cells. After it will go to the endosome, lysosomes. Finally, it's like high concentration of H2S. The acid will be reduction, become like amine. Amine will be like clear the electron transfer. After that, the cleavage, the breaking the bond. After that, we can see the drug will be released. So specifically, it will kill the cancers in the doxorubicin. Next, further we check like apoptosis mechanism using the like a fluorescent microscopy to increase the time. For example, initially we check like within 2 hours specifically have emission in the nucleus. But if you increase the incubation time about like 10 hours or 12 hours or 15 hours, we can see the cell morphology and the nucleus structure is damaging. So it's like another evidence for the, we can see about 10 or 12 hours means the nucleus is destroyed. So this we can see the apoptosis mechanism. So it's clearly indicated the cells are damaged in the nucleus morphology. Further we check like another evidence for the anaxine V and FAT-CPA doubling staining and with the photographic image. So we can see the control group and the doxorubicin nanoparticle, the tumor size suppressed compared with the free drops. And further we check the double staining, right? So this one is only for the control group, so we cannot see any apoptosis. But we can compare with the free dose and the doxorubicin nanoparticle. These two images we can see here. This is like only for the 7.5% compared with the doxorubicin nanoparticle. So we can see like 29% apoptosis. So free dose only for the 7%, but if you doxorubicin nanoparticle with using the H2S responsive, the clear strategy is like maybe around 30% is apoptosis. After that, further we check anti-tumor efficacy also. So here we can see the control group. The control group only PPS. So still the tumor volume is increasing. And further we can check with the free dose and without doxorubicin nanoparticle, we can see still is growing. But finally, the doxorubicin nanoparticle you can see like maybe 68 points this efficacy compared with the free dose. But the tumor weight also is compared with the free dose is like completely suppressing, and the body weight also is there is no change using a different functional group and compared with the control and the free dose. After that, we collect the tumor, this tumor to using the histochemical analysis to make sure this one is like what is the structure of the cells, like a nucleus structure. Further, we check like a histochemical analysis. So there is a two chemical analysis, one is H&E staining, and another one is like a tunnel staining. Here we can see the morphology and the coloring. In this, like a tunnel means like we can see only for like in the free dogs as a dead cell, right? So in the blue in the tunnel staining, we can see dead cell only as a green emission. So here, this is the control group. We cannot see any emission, right? There is no dead cells. But the free dogs, we can see very little dead cells compared, because the efficacy is compared with the dose-loaded nanoparticle is very less. But here there is no dose-loaded nanoparticle. We cannot see any green emission because here no dead cells. But here we can see the dose-loaded mesoporosylica nanoparticle. So we can see it's like a compared with the dose have many apoptosis under the dead cells. So we can see it very clearly. So both these experiments so very clearly indicate that so the nanoparticles specifically released in the high concentration of H2S, specifically in the colon or maybe ovarian cancer only, drug will be released as a targeting in the nucleus drug. So this is my conclusion. So in this material, the mesoporosylica nanoparticle as a new biocompatible as a nanocarrier, and there is no drug leakage, and the cell viability also compared with the normal cell and the ELA cell also specifically is released in the colon and ovarian cancer cells only, and then the cell image and the anti-tumor efficacy also compared with the free dogs is a more efficacy. So thanks to Professor Pinching Lai and my PhD advisor Professor Usupa. Thank you for your kind attention. So if anybody has a question, so you can call.
Thank you for your valuable lecture, sir. Participants, now you may clarify your queries.
Students, if you have any questions, you can ask, please. You have to be interactive, students are as well as the scholars. Yeah, from bio side, Ratna or anybody else from biotech? Any clarifications you can ask. Fine, sir. In the absence of any queries, we once again thank you for your.
If anybody has a questions, maybe you can email me.
Yeah, that should be fine. And also, we are interested about your valuable information on the admission procedures in your or scholarship opportunities in your esteemed university. Really, it will be quite useful for our PG students as well as UG students. Thanks a lot, sir, once again.
Sure, sir.
Thank you, sir.
HOD chemical, yeah, thank you. HOD AC, sir. HOD is there?
No, Bhaskar.
Yeah, so can you move to the next lecture, sir? Sir, you can.
Okay, sure.
Yeah. Thank you, Professor. Thank you, Dr. P. Venkateswara.
Thank you.
Let's proceed with the next session.
Now, Dr. B. Muthuraman, Assistant Professor and Head in Charge, Department of Energy, University of Madras, Chennai, will be delivering a lecture for 40 minutes. Now, I'd like to call upon Ms. Preeta, Applied Chemistry Department, SVCE, to introduce the chief guest, Dr. B. Muthuraman.
Thank you, Anusha. Good morning to all. I'm Preeta from the Department of Applied Chemistry. It's my pleasure to introduce our speaker, Dr. B. Muthuraman, Assistant Professor and Head in Charge, Department of Energy, University of Madras, Chennai. He has a wide knowledge in the field of energy and is more specialized in the fields like dye solar cells, electrolytes, and cathode materials. He has received many scholarships during his post-graduation. He has also received the Senior Research Fellowship Award by CSIR, New Delhi, and the Best Student Achiever Award by University of Madras, Chennai. He has many publications in various reputed journals. Currently, he is having 4 projects funded by various agencies. He is a postdoctoral fellow in Royal Institute of Technology, Stockholm, Sweden, and postdoctoral research fellow, Queensland University of Technology, Brisbane, Australia. He is a visiting scientist to Chonam National University, Korea, and Australian Academy of Science, Australia. Now it's my privilege to welcome such an eminent person for the day. Sir, welcome sir. Now the session is yours.
Bhaskar sir?
Yeah, Mani, yes, Manigandan.
Yes sir, in speaker start.
And Dr. Muthuraman, I'll check sir, I'll check.
Okay.
Sometime before Dr. Muthuraman was there, I'll just make a call to Dr. Muthuraman. I think he is having some connectivity issue. I request the participants to just a few minutes. Madam Preeta.
Yes, sir.
Since the speaker has joined just now, I request once again.
Okay, sir, sure.
Thank you.
A very good morning to one and all. It's my pleasure to introduce our speaker, Dr. V. Muthuraman, Assistant Professor and Head in Charge, Department of Energy, University of Madras, Chennai. He has a wide knowledge in the field of energy and is more specialized in the fields like dye solar cells, electrolytes and cathode materials. He has received many scholarships during his post-graduation, and also he has received the Senior Research Fellowship Award by CSIR, New Delhi, and the Best Student Achiever Award by University of Madras, Chennai. He has many publications in various reputed journals and currently is having 4 projects by various funding agencies. He is a postdoctoral fellow in Royal Institute of Technology, Stockholm, Sweden, and postdoctoral research fellow, Queensland University of Technology, Brisbane, Australia. He is a visiting scientist to Toronto National University, Korea, and Australian Academy of Science, Australia. It's my privilege to welcome such an eminent person for the day. Welcome, sir. Now the session is yours.
Good morning, madam. Thank you for your generous introduction.
Thank you, sir.
Yeah. So, am I clear? I said, am I sounding clear?
Yes, sir.
You're audible, sir.
Yeah, thank you, sir. Okay. So it's been an immense pleasure to join with you in this occasion, and I think it is much appreciated towards the organizers for having been invited me to this wonderful international conferences. And thanks once again for the organizers for inviting me and giving me this opportunity. Thank you. So I will present more. Share slide. So, can you see my slide?
It's visible, sir.
Yeah, okay. Nice, good.
It's visible, sir.
Thank you. So I'll be taking you maybe 40 minutes around. I'll be talking about some materials which we have made in our lab and we have used for this. So advanced materials for green energy devices. So you know very well the material research may be quenched with various materials that have been quenched for maybe hello? Slide is moving, am I right?
No, sir. The slide is not moving.
No. Now?
No.
Yeah, yes, sir. Moving, sir.
Okay.
Yes.
Okay.
Sir, you can put a slide show, sir.
No, slide show is not moving.
Okay, sir. Okay, then okay, sir.
See? It was not moving, right? Is it moving?
No, sir.
No, sir. The first slide.
Yeah, it is moving, sir, now.
Moving. Yes, sir.
Can I ask?
Screen is blank, sir.
No.
Now.
Yeah.
Now it is visible.
Yeah, thanks. Okay. So, material research of the energy needs are in various methods for crunching the energy needs of there are so many methods for methods of preparations or the choices to make the materials we need for the energy. So, for example, the catalysis by nanoscale and using interfaces to manipulate energy carriers and linking structures and functions at the nanoscale. So then makes an assembly and architecture of nanoscale structures for the energy devices, either for the device like electrodes or devices, something like that. And of late, we have theoretical modeling and simulation of energy nanosensors, shortly called as computational. So like lots of work is going on that one, and then scalable synthesis methods. So example of mainly used, for example, we deal with this one here, the energy applications by of the nanomaterials. So first one is a photovoltaic generation and water splitting. So this is kind of water splitting either by photocatalysis, or this is the same photocatalysis also used for the photovoltaic generations. So they follow a radiation transport to maximize absorption. So it may be a two-phase flow, electrochemical transport, and same way the catalytic nanostrike for used for the hydrogen production. So this is like a mass transport, like heat transfer. So this was a small-scale thermodynamics. This is also a two-phase flow. So materials for energy applications, particularly of nanomaterials, of photovoltaic and solar cells. Basically, there are many types of solar cells. So here it's the main two types here. One is silicon solar cell and second one is dye-sensitized solar cell. So here we are going to talk about the dye-sensitized solar cells materials. So it's maybe a newer material and it's a new technology. Now it's becoming inexpensive to fabricate, and it's highly flexible also. So energy from the sun. So everybody knows this photosynthesis. It's an everyday occurrence in the plants to generation for this prepare food to the process to produce starch. So then the solar, you can see a picture there. So it may look like a solar cell, but it's not a solar cell. So this kind of technologies are called a concentrated solar power. So this is a mirror. So the mirror, you can see the rays going up. So this mirror reflects the sunlight on a particular point to get this technology is used in the places where you get feeble sunlight. So here the rays converge at the top of the tower to get the required intensity, and from there you get the conversion. The light harvesting takes place, and from there the conversion takes place. And then the solar electricity, which with the domestic users. So all these places you have seen the day-to-day occurrence, we come across these applications of solar energy. So what we lack? So the main thing is storage. So we don't store, or we never store a sunlight to use it for in future. So like we never store a sunlight. So only thing is we use is for your daily is for drying clothes. Other than that, we never use for anything. So main problem is storage. So how you can manage this storage, how you can make this a large amount of energy, which is green and free. So you are not going to pay anyone for a sunlight, and it is also most environmentally friendly. So how to harvest, so how to make use of this, that scientists started looking on that one, and thus came the solar cell technologies. So initially it is of a silicon solar cell. So then a thin film solar cell, which is known as CIGS, stands for copper, indium, gallium selenide. And then thin film solar cells like cadmium sulfide and cadmium telluride. So this is like highly toxic. So now it's not using that much. So these are initially it was too expensive. So scientists started working on that to improve its efficiency and also to reduce its cost. So then in 1991, there was an historic publication in Nature published by Becker Craxwell and Brian O'Regan. So it is from EPFL Lausanne, Switzerland. So this is the first of its kind of a low-cost, high-efficiency solar cell based on a dye. Dye is the colored material, so that is used to sensitize to the N-type semiconductor, which is it will be observed on an N-type semiconductor, known as titanium dioxide. So how it looks like, as I told you, it was 1991. These two gentlemen, O'Regan and Graphical, so found out this efficient Dyson's photoelectrochemical cell. So it consists of a highly porous nature and a titanium dioxide electrode sensitized with a monolayer. It's a dye-adsorbed one. So the dye is adsorbed on the surface. So this is also called as a great cell. So having an overall light to conversion efficiency of that time is 11% efficiency in diffuse daylight. So it is the solar cell is measured in the international way, like it has a standard way of measuring, like 1 sun refers to 1,000 watts per square meter and 25 degrees centigrade. So AM 1.5 stands for the angle at which the instant light makes with the atmosphere. So this is how they measure the initial solar cell. So as you know, a typical electrochemical cell, like it will consist of a cathode, anode, and an electrolyte in between. The same way, the photoelectrochemical cell will also have a cathode, anode, and an electrolyte to connect between the electrodes. So this is a schematic representation how a dye-sensitized solar cell looks. So we will come back again to this one. So electrolyte, what is an electrolyte? Is a chemical system that provides an electrolytic contact between the solar cell electrodes and may exist in a solid, liquid, or a solution form. So what are the major limitations of using a liquid electrolyte in dye-sensitized solar cell? Is the long-term operation, and it is highly susceptible for atmospheric degradation. So like evaporation, decomposition, and also it is highly corrosive with the electrodes. So in order to overcome all these deficiencies, like I started to work on this one. So this is the chronological order how the present state has been improved by one step by step. So in 1991, so a low cost, high efficiency I told you already. So this is one. Just a minute, I'm not sure. Look, so in 1991, as I told you, it is made with a liquid electrolyte. It is highly volatile. So in 2001, they changed this after a long time. They changed the liquid electrolyte, the polymer electrolyte. In this, they made with they want to improve the stability. Improve the stability in the sense they improve the evaporation, or usually we have the redox materials. We have usually a redox couple is made of that time. It is made of iodine iodide redox couple, which is highly which sublimes immediately. So in order to prevent the sublimation, they added a polymer electrolyte. So still there was then added an additive. So they made an iodine iodide free. Then the cobalt polypridine redox mediators. Then came the ionic liquids, that is called as molten salt mixtures. So evaluation. So evolution of electrolytes for its use in dye-sensitized solar cell, as I told you. So it mentioned the electrolyte maintains an electrolytic contact between the electrodes. So we'll see. So here, as I told you, the liquid electrolyte has so many kind of a limitation. It is highly degraded and highly it is unstable. So then came, as I told you, it produces then it's a slowly developed with the polymer electrolytes in order to make its stability increase its stability. So the polymer electrolytes may be generally here we defined as a membrane. So here it's like used as a membrane that possesses the transport properties comparable with that of liquid electrolyte, and the more advantages of that is more highly flexible, and it is also like corrosion resistant, leakage proof, and non-combustible reaction products. The electrodes, all these things giving a favorable qualities to qualify as an electrolyte. So it became a choice to use a polymer, particularly a conducting polymer. So the major candidate which you are going to see in this presentation is polyethylene oxide, polyvinylidene fluoride, and polyvinylidene fluoride copolymer. So these are the types of electrolyte systems which we prepare. The one is the PEO-based electrolytes and the PVDF based electrolytes, and the third one is the polymer blends, the blending of two different polymers. So then comes the multi-wall carbon nanotubes with it. Then came the molten salt mixtures, otherwise called as Ionic liquids. Then this detergent based. We'll see one by one. So in 2001, as I told you, A.F. Nogueira and Marco Di Poli, so they are the first to introduce the polymer in the pre-existing electrolyte. So this is the first time they introduced the polymer. They got like around 4.4 to 5% efficiency, but the stability improved much, but the efficiency went down. So then the Japanese group introduced iodine complexing agent. So it is nothing but like Professor Arakawa introduced iodine complexing agent. It forms a charge transfer complex. Charge transfer complex is nothing but intermolecular charge transfer complex. Forming is explained by the interaction of between the HOMO of the donor and the LUMO of the acceptor. There will be an interchange of charges. There will be exchange of charges will be there. So there will be there will not be any bond will be formed. It is just an exchange of charges. So greater the overlap will be when it is the ionization energy of the donor is small and the electron affinity of the acceptor is large. So this is how the charge transfer complex forms. It prevents the sublimation of iodine to a greater extent. So then came the solid polymer electrolytes. So electrolytes like polyethylene oxide with the redox materials, this also gave only 4 to 4.5% efficiency, and it doesn't make much improvement on the existing system. Then came the gel polymer electrolytes. So they made with the gelling agents like a potassium propylene carbonate and ethylene carbonate as a gelling agent. So with the reduction, so this having a very good like a stable as it channelizes the flow of electrons. So and this also to some extent it reduces the recombinations losses. So what are the advantages? As I told you, it channelizes the flow electrons. So there will be a good interconnectivity between the electrons, and also have an outstanding, it's a long-term stability also increase. So these are the advantages of using a gel polymer electrolyte. So from our research group, we also contributed for that one, which is iron complexing agent with the redox couple. So you can see a stick-like structure. That is the polymer. So that is the polymer which you can see here. So we got like a 4.1% efficiency. So this is how we make the polymer electrolyte. We put the polymer in a solvent, and we make it as a depending upon the requirement. We make it either it is highly viscous or low viscous, or the gelling type, or it's more like a solid. So depending upon the requirement, depending upon the ease of, depending upon the device, we play around this mechanism or we play around this preparation method. So it's taken either we change the solvent or this one. So, but this is the general one. So the electrolyte materials immersed or stirred at a given solvent for around depending upon the temperature requirement. So resulting will be the polymer electrolyte. You can make it as a film by either by solution casting, or by you can use it as a viscous liquid, or you can use it as a gel. So this is how it looks like in some pictures. You can see it is like a spherulite structures. You can see there it can forms spherulite structures, and this one is having a very good interconnectivity with the dye. Then we moved on to prepare our new polymer. So it is a hyperbranched polymer. So in order to check whether the polymer plays on, but still we didn't succeed. We just we got also 4.2% efficiency. So this is how it works. The hyperbranched polymer, you can see the redox material like hops through the chain. Like hops means it is like from one chain to other. It just jumps from one to out. So it kind of a segmental motion along the chain. So it reduces the sublimation of iron, but the efficiency went down. So then we went for the polymer. You can see a beautiful pictures there. So it's like a nano rods around 30 to 35 nanometers. So you can see a nano brush like thing. So you can see the formation of the nano rods by this one, in this is device is made with carbon counteractive. So this one is highly stable, and we got 4.3% efficiency. And this is because of this nano, we got a high current, short circuit current. So this is the reaction. How you can see elliptical structure. So this is how the charge transfer complex formation occurs. You can see the exchange of charges between the iodine and the compound. So this way it forms it forms an attraction. It doesn't form any bond. So this kind of attraction is called charge transfer complex. So then we look on to the multi-wall carbon nanotube. This advantages of this one is it channelizes the multi-wall carbon nanotube channelizes the ejected electrons. So the loss of electrons through recombination has been very much reduced. Hence the short circuit current increase, but the voltage dropped down. So the efficiency again, it was really around below the 5% mark. So then we moved on to the solid state electrolyte. So we made a fast ion conductors like solid state electrolyte, silver ion conductors. So we want to remove the problematic liquid part. So it is a completely solid electrolyte. So then we made a viscous detergent. So you know what is a detergent? So we made a kind of a detergent-based composite electrolyte with the iodine complexing agent. So here you can see this is the first time of its kind. It's a new technology. It's a new technique, but the efficiency is very, very low. You can see this exactly mimics a leaf. Like leaf will have a cytoplasm, mitochondria, Golgi bodies, a cell wall thing. Same way here, the matrix is the detergent matrix forms the cytoplasm, and the fast ion conductors forms like a powerhouses of a cell, and the chlorophyll forms the dye. So it exactly mimics, and the electrochemical pump is the iodine-iodine redox couple. So all these things mimics exactly the leaf, and it was a very good technique, but the efficiency and the stability is very, very good. The efficiency is very low. So then we move on to the inorganic nanoparticles, introduction of the nanoparticles recombination. So this can reduce a recombination. What does mean by recombination loss is the unwanted discharge of electrons. So we need the electrons in the allotted or permitted way, so that you can harvest the maximum number of electrons and thereby you get an efficiency increase. But if you get the electrons loss on the way or in the backwards, so that leads to the recombination. That loss is called recombination losses. So with this inorganic filter, you have enhanced diffusion coefficient, and it also has a very good channelizers, of course, I told you. So this stops an increased exchange mechanism, like a Grotius type of mechanism, means like a hopping type of mechanism. So this way, like introduction of nanoparticles doesn't yield much of a benefit. Then we went for the room temperature ionic liquids, so which is also called as green solvents. So green solvents either called as ionic liquids or as molten salt. So this has almost every favorable qualities to qualify as an electrolyte. So it has some high, very nice and good physical-chemical properties and good chemical and electrochemical stability, non-flammability, a wide electrochemical window, and nice, good viscous, nice and low viscous, and negligible vapor pressure, and also a very good high conductivity also. So, and also it is almost thermal stability. So this qualifies. So we just ventured into the use of this ionic liquids into our electrolyte part in order to overcome the deficiencies. So this is the solid state as the complete solid, as I told you before. So you can see here. So this is a beautiful geometry that you can see. Each small square is an independent solar cell. So you can see a 4 small solar cell in a single glass. So it's a nice geometry. You can see in this one, both the anode and the cathode in a single plate. So the below strip, long strip is the cathode, and the above small strip is the anode. So this is the mechanism. This is this geometry is we first time we made it, but the efficiency is very low. Sorry, the efficiency is 4.5% efficient, but the stability is very low. It doesn't even last for a day, so it's highly unstable. So then we look for the alternate redox. The people like and the Sackford group from Uppsala, they first made a cobalt electrolyte. They changed the iron redox couple with the cobalt. So first time they got like 6.7% efficiency and also with the good stability. This achieved is through the adjusting the band gap of the dye to match the electrolyte. So this they used a new dye also, D35. So this made the people to work on a different direction or a different insight, to see a different way. So they worked on this one. So recent developments is like new redox couple like a cobalt has been made, and now also of late we have perovskite solar cells. A lot of work is going on with perovskite solar cells, and developed a new polymer-based cobalt system now. So we also made a polymer-based, cobalt-based polymer nanocomposite. So this one is like we got 8.1% efficiency. This is a very good for indoor applications. It works in the in our like indoor lights. In the normal indoor lights, it will work nicely. So we got this one as an interview was published in the US magazine. So then we got the European magazine also interviewed us, and we made that one. And this that year we are the top 5 of the journal of that published the top 5. So we went into the top 5 highly cited altimetrics. So you can see this one has a very good fill factor, and the curve shows the performance of the solar cell. This curve is called the current voltage curve or IV curve. So here you can see the cobalt with the polymer, it got 8.1% efficiency and the indoor light. So it's highly stable. So this electrolyte we have given to a company. So G24i, which they make flexible solar cells. So we give that one. So this forms in a mechanism. It's a kind of polarization takes place with the redox materials, and from the charges exchange takes place. So it is. This is how it works. So that's one. Then we went to the molten salt, as I told you. So with the polymer. So this is also the polymer. The molten salts are made into with the polymer moiety and made a new kind of a composite. So this is also highly stable, and this is the first time you get a molten salt with a polymer of very good efficiency also. So it's published in ACS. So that's why it's nice. So we got the concept as a molten salt is a new concept we introduced. So then now we started working on the materials of the, we are just venturing making it a plastic solar cells. I mean a flexible solar cell. So on depending upon the temperature, it's around 200. So we made a temperature studies of the cathode or the flexible materials recently. So with using a PDOT is a polymer electrode. So it's a PDOT is a polyethylene dioxide, so which we use it as a flexible electrode. So we have a very good we studied on that one, published in RC recently. So then we made some clusters for the hydrogen generation or hydrogen production. So published in JPC now recently. And with this brown minerite, we made it for photocatalysis and also its supercapacitor applications. So it's a published, and this one is like it's got a very good efficiency. Brown minerite is from a natural ore, so this has a very good natural kind of healing photocatalytic property. So this is scientific reports. So recent, like we have started working on this supercapacitors with using green materials of graphene oxide or reduced graphene oxide. So device. So the shown which I shown the materials can be, or the electrolytes which we measured, which we prepare the above ways can be used for the dye-sensitized solar cells or batteries or etc. depending upon the applications. So this is the way we can make the cells in our lab. So you can do like just a 1 centimeter by 1 centimeter cells dimensions. So this is how the test cells look like. So it forms a perfect rain cell. The dye-sensitized solar cell is more energetic than the silicon solar cell. It may be more efficient, but it is more energetic because dye-sensitized solar cell works very good in diffused light. So it starts early in the morning, then it goes up to late evening, but the silicon solar cells start after the sun becomes intense and just go off after it becomes dark. So it may be high efficient, but less energetic, but this is more energetic. So you can see this is how its application. You can see this is the diagonal photos, like this building is from the Australian Central Council for Industrial Research. They have the building fluorinated dye-sensitized solar cell, and also you can see these window glasses has been replaced with the dye solar cell, and this one is shown in Japan. This lights has been produced for that time in Japan for remote places. So you can see the applications, like you can see this is, as I told you, we gave this Polymer Electrolyte for this bag company only. So, and also they make a flexible keypads. So this is like when you can put your mobile or laptop and you can charge while you walk. So it's highly flexible also, and but the efficiency still has to, the module efficiency is less compared to the lab efficiency. So still lots of work is going on this one to improve the efficiency and also the robust nature of the cell. So these are the detail how it works. You can see the dye-sensitized solar cell here. It will have you can see the schematic representation. The anode is one which you will be coating with the TiO2 paste, above which a dye is absorbed. So So that forms the anode, and the cathode is one where you have platinum electrodes sputtered sputtered on FTO. FTO is a conducting glass. So the conducting glass, how you make a conducting glass is nothing but the normal glass is made in the conductive by either by a thin film coating of a conducting materials like a tin fluorine or tin oxide or indium tin oxide. So this is called as FTOs or ITO. So these glasses are made into conductive on one side and can be used as in the solar cell as electrodes. So the anode is one which contains the titanium, diads of titanium, also the anode on DIO on conducting glass is the anode, and platinum coated on conducting glass is the cathode. And the redox is nothing but the 3 parts of iodine and 1 part of iodide salt in any alcohol or any solvent like acetonitrile, ethanol, any solvent. Okay, so you can see how it the thickness of the electrolyte coating will be a maximum of 20 micron. You can see lots and lots of reactions going on between this 20 micron thickness by electrostatic interaction, bulk effect, transport by diffusion, and like a grain boundary effect, and also you will have the porosity nature. So it depends upon the porosity nature, the flow of electrons occurs, and the recombinations and losses. All these things occurs between this, like maybe within these 20, not even 20, it will be around 17 to 18 micron thickness. Okay, so you can see a graph on the right side. This is how you measure the performance of a Dyson state solar cell. So you make a solar cell and measure it with a light source with a multimeter. You get a current and a voltage and plotting with different resistance. But if you plot it in a IV tracer, it will give you everything. So the x-axis gives the short open circuit voltage, and the y-axis gives the short circuit current, and the maximum point gives the power max, which is nothing but the maximum power you can get from the cell under working condition. Okay, so this is how this reaction goes on. Because there is some animations, but it is not working. I don't know whether it works because the slide is not changing. So you can see a lot of reactions is going on the anode part, the electrode, the cathode part, and the electrolyte part. So which leads everything ultimately leads to a module. So you can see the solar installations in around India. You can see Tamil Nadu is nowhere there. So we should work a lot to improve our solar cell setup and work towards the greener energy to make more installations. We should also grab a sizable part from this portion. So like at least like we should aim for 10 because it's like we are nowhere there. So presently we are working on ceramic electrodes and ternary compounds and alternative counter electrodes for the supercapacitor as well as for solar cells, and also we are working for conductive polymers for flexible counter electrodes, and also some gel-based electrolyte systems, and recently we have like started working in the computational modeling of our devices. So we had some collaborative research with the EA. So they are the software. They provide some analytics details regarding the analytics about the devices. So we just exchange our views, and we are discussing and producing some theoretical modeling works is going on now. So India is, you can see the Kochi is the first Indian airport to be fully solar powered airport. So this is not the money that lacks, but the will to change towards the greener energy. So you should have the will to change towards the greener energy. So I can acknowledge my students and the funding agency, DST, UGC, DST, RUSA, CSAR for my research works. So thank you. Hello.
Thank you, sir, for your excellent lecture. Now it is open for audience for any questions or clarifications. So people can interact. If you have any clarifications, you can ask Professor Muthuraman.
Hello, sir. Good morning.
Good morning, sir.
Sir, is my voice audible, sir?
Yes, sir.
Yeah, sir. My name is Vishnu Prasad. I am a faculty in Chemical Engineering Department. Sir, I am having a small doubt, sir. Hello?
Yes, sir. Tell me.
Actually, one of my MTech students did a work in the last year with the cooling of solar panels. Okay. In the literature, we have found that the efficiency of the solar panel will decreases when it gets overheated. So we fabricated a cooling system in such a way that the nanofluid, the heat transfer fluid, will pass through the channel which is packed. That means which is arranged very close to the solar panel. Below, that means the top surface is exposed to sunlight and the bottom surface is exposed to a what I call a nanofluid channel. In the channel, the nanofluid will pass and it will take the heat. So we have found a very low improvement in efficiency, and we finalized that it is actually due to the improper heat transfer between the solar panel and the nanofluid. That means the bottom side of the panel is not actually a smooth surface. It is having some imperfect surface, something like some not. It is actually a smooth surface. So we have found some physical difficulty in absorbing the heat from the solar panel. So can you give some suggestion in order to improve this particular process? Whether actually we are going to improve the project in this area, whether I am going in the correct track or not. I need some suggestions from you, sir. Otherwise, you can give some other ideas in order to improve this efficiency by cooling.
Okay, sir. Sir, can I ask you, like, you put a closed, like a spiral-shaped tubes below the backside, am I right?
Yeah. Actually, spiral-shaped tubes in the backside, and the spiral-shaped tube is not actually going directly. We make a phase change material packed below this panel, and inside this phase change material, this particular coil is going like that.
Yeah, I got it. Like, can I ask you, like, you put it after the protective atmospheric layer or before the protective atmospheric layer?
Sir, actually, we purchased a solar panel. Then we did our experiment like that. We cannot know how to remove. Actually, the person told one insulating layer will be there. The heat transfer will be not proper if the insulating layer is there. That's why I'm asking. Can you
he said he said is right. So you should remove. You should pack your cooling system after the electrode. And then, because you have a protective layer, yes, your cell is made to be a protective sealant to prevent it from the atmospheric degradation. So you should, I suppose your coolant is highly stable, am I right?
Yeah, yes, sir.
So you should place this cooling, the spiral tube below the in close contact below the counter electrode, I mean backside. And first, next one, and it should be the your selection of fluid should be in such a way it should not affect the scattering light.
Okay.
All right, because you need some light from the back scattering.
Okay.
Okay, so back scattering also improves the efficiency to some extent.
Okay, sir.
Because the light, the stray lights which goes beyond or which goes backside will also again gets reflected back.
Okay.
So for this one, in Dyson solar cell, they started using a scattering layer.
Okay, sir.
So which absorbs the scattering layer, again goes back and again this turns back into the dye.
Okay, sir.
So here you can make either a scattering layer, and this one, your cooling system should be packed in such a way it should touch the in close proximity with the counter, in the electrode. Because you have placed your cooling system after the protective layer, means there will be no effect, and the effect will also be less, and also your system will also be prone to the atmospheric degradation.
Okay, sir. Okay.
And one second thing is like there is a threshold limit up to which your solar cell increases the efficiency when the temperature rises.
Okay.
Okay, so if for example, if your temperature is 20, your silicon solar cell will not work much.
Yes.
If it goes up to 32, it starts working very good.
Yes, sir.
So in that case, like you need a higher temperature.
Okay.
So as far as temperature is concerned, usually cells they will be stable up to 60 degrees centigrade.
Okay, sir.
So up to 50 degrees centigrade, it's the below, if it works below the 40 degree, it will be stable for a long time and it will be durable for a long time. But if it exceeds 50, means the efficiency will go up. There will be like going up, and there will not be very stable. So it will be like ups and downs. And the stability and the durability of the cell will also reduce.
Okay.
So the cooling pack is only necessary for the regions where you get the temperature above 45 or something like that.
Okay, sir.
Okay.
Thank you, sir.
Thank you. Hello.
Yes, please. Any other questions, please? Madam Preeta is there? Okay, fine. HOD applied chemistry, sir?
No, it's okay.
Yeah. Preeta ma'am, you can, if there are no questions, you can just thank the professor. Ram. HOD is HOD want to say anything?
Yes, sir. Sir, HOD, sir.
No, we can proceed.
Okay, sir. Thank you, sir.
So now I take this opportunity to thank Muthuraman sir for giving a wonderful lecture. Thank you so much, sir.
Thank you, Professor.
Thank you, ma'am. Thank you, sir. Thank you for the nice opportunity. Thank you for being with this conference. Thank you, sir.
Thank you, sir. Now over to Lavanya or Anusha.
Now I request all the participants to join their respective tracks. Participants can join their respective tracks. The session will begin soon.